So last time we talked about the rules, how to find the absolute configuration of a chiral carbon, and we agreed. We rank the 4 atoms or groups that are attached to the chiral center according to the atomic number. The one that has highest atomic number, that will be of highest priority. We orient the molecule so that the lowest priority group is away from us, so away from you in this case. And then if you are going from the highest priority to the lowest priority in a clockwise manner, that will be an R configuration. If you are going in a counterclockwise, that will be an S configuration. So let's practice. For instance, if we are looking at these 2 enantiomers, which one has the highest priority? The oxygen. So that's 1. Where is the second in priority? CH2, CH3. I have the carbon to be bonded to carbon, hydrogen, hydrogen. The carbon is bonded to 3 hydrogen. So I have 1, 2, 3. Where is the lowest priority group? Hydrogen. It is a dashed bond. It means that hydrogen is away from us. So the molecule is already oriented so that the lowest priority group is away from us. Going from 1 to 2 to 3, from highest priority to lowest priority, am I going clockwise or counterclockwise? Counter. Therefore, this is an S. Now, if I am looking here, where is group number 1? Highest priority, OH. Second, CH2, CH3, then CH3. Hydrogen, the lowest priority, is away from me. Therefore, going from highest priority to lowest priority, I am going clockwise. That will be an R configuration. So this is S2 butanol. This is R2 butanol. Let's look, before we look at another example. It's very important to know that the R and S configurations are not associated with the sign of rotation of the plane of polarized light. So if it is an R, it doesn't tell you that it is going to rotate it in the minus direction or in the positive direction. All you know, if one enantiomer is rotating in the minus, the other one is in the positive. Now let's find the chirality center. Where is the absolute configuration of the chirality center here? Where is the chirality center? This carbon, it is attached to hydrogen, CH3. Let's do this on the board. I need to find the priority of the groups that are attached to the methyl cyclohexene, the 4-methyl cyclohexene. Now, priority. I am looking at this carbon. So where is priority number 1? Well, I have a carbon, carbon, carbon. This carbon is bonded to hydrogen, hydrogen, hydrogen. This carbon is bonded to carbon, hydrogen, hydrogen. This carbon is bonded to carbon, hydrogen, hydrogen. So I need to look beyond. And now between this carbon, and this carbon, which one is priority number 3 or the lowest? Now I need to look at these 2. So this carbon is bonded to carbon, hydrogen, hydrogen. This carbon is bonded to carbon, hydrogen, hydrogen. Now I am looking at these 2 carbons to this side. So I'm looking at this one. This carbon is bonded to what? Carbon, hydrogen, hydrogen. While this carbon is bonded to what? Carbon, carbon, hydrogen. Therefore, which one has the higher priority? This is 1. This is 2. I have 1, 2, 3. Am I going clockwise or counterclockwise? Clockwise. Therefore, it is an R configuration. Okay. Now, we're going to talk about a new type of projection which is called the Fischer projection. in the Fischer projection, we are not going to be drawing bolded bonds and dashed bonds. But it is very important to be aware of the terminology of a Fischer projection and to go from a three-dimensional shape into a Fischer projection, you need to orient the molecule so that the horizontal bonds are towards you and the vertical bonds are away from you. From where you are sitting, you are looking at this molecule in the, you have the orientation of the molecule to be correct. From where I am standing, that will be the wrong configuration. I have to rotate it from where I am standing so that I have the horizontal bonds directed towards me and the vertical bonds away from me. From your side, that will do it. I have the horizontal bonds, they are towards you, and the vertical bonds are away from you. In a Fischer projection, after you orient the molecule so that the horizontal bonds are towards you and the vertical bonds are away from you, you take a projection on the plane, and that will be a cross. When you have this cross, you need to know that the horizontal bonds are towards you and the vertical bonds are away from you. We're going to talk later, probably during this lecture or next lecture, how do we go from for instance, a Sawhorse projection where you have two chirality centers into a Fischer projection. And we are going to do that step by step. So a Fischer projection, when you are looking at a Fischer projection, you are not having bolded and dashed bonds, you are having a cross. And you need to know that all the bonds that are horizontal are towards you, and all the bonds that are vertical are away from you. That applies also if you have two chirality centers. So if I have here, let's say this is CH3, H, OH, Br, H, CH3. I am drawing it in a Fischer projection. This one is this, C, bolded. These bonds that are horizontal are towards you. These bonds are away from you. So in a Fischer projection, the horizontal bonds are towards you and the vertical bonds are away from you. Now, properties of enantiomers. When you are looking, yes?
At that molecule, the bond between the carbon-carbon, should it be away from us also? Should it be dashed?
No. We're going to get back to that in the next lecture or towards the end of this lecture. And you will see that when I build the model, actually. I'm going to be building a model, and then you will see that it is not away from you. Now, regarding the properties of enantiomers. Enantiomers, they have the same physical properties. So they have the same melting point. They have the same boiling point. They have the same density. They have the same polarity. And that makes it very hard to separate enantiomers, as I referred to last time. The only difference in terms of properties, any property that is coming from the three-dimensional shape of the molecule. So for instance, and before we go into an example, that means any activity that is biological or physiological, of physiological properties, it will be different from one enantiomer to the other enantiomer. For instance, the odor, the smell of one enantiomer will be totally different from the second enantiomer. What we have here, the two enantiomers, the minus carbon and the plus carbon. So one is rotating in the negative direction, the other one is rotating in the positive direction. The one that is rotating in the negative direction, that has an odor of spearmint oil. The other one has the caraway seed oil. And why do you have different odors? Well, because the molecule that is chiral, it is fitting in a chiral receptor. The receptors are chiral. So then you are having one enantiomer to be fitting one chiral receptor, while the other enantiomer cannot fit that chiral center. The olfactory receptors that we have in our noses are in fact chiral. That's why we will smell one enantiomer caraway seed oil and the other enantiomer with different odor, because it will be fitting a different olfactory chiral center. So what we know about enantiomers till now, they have the same physical properties, same melting point, same boiling point, same density. When you go into the lab later, probably some of you will take chemistry 210 or chemistry 225, and you will try to do TLC, thin layer chromatography, or column chromatography. If you try to do that on enantiomers, they will be moving exactly the same. And again, that makes it very hard to separate two enantiomers. The only difference is any property that depends on the three-dimensional shape. And also we know that one enantiomer will be rotating in the positive direction, the plane of polarized light, while the second enantiomer will be rotating in the negative direction. Okay. Ibuprofen. Ibuprofen is chiral. But when we go and we buy ibuprofen, we are actually buying it as a racemic mixture. And there is one enantiomer, which is the S enantiomer, that has the analgesic and anti-inflammatory properties, while the R enantiomer does not have these properties. So when we are swallowing an ibuprofen tablet, which is a racemic mixture, we are actually swallowing 50%, or 50% of that tablet has the properties, the anti-inflammatory properties. The other enantiomer, which is the R enantiomer, fortunately, is not harmful. And more fortunately, that we have an enzyme in our body that will convert the R enantiomer into an S enantiomer. So effectively, after we swallow it, we are having the 100% of the tablet to be having to be an S enantiomer. So for that reason, people will not go into the lab and try to separate the S enantiomer and R enantiomer. Okay, there is no reason to do that. Now, I'm going to talk about chirality axis. Till now, what we talked about in terms of chirality, we said we need to have a chiral center. And we have 4 different groups so that the molecule will be chiral. But you can have different type of chiral molecules where they exhibit a chirality axis. So you do not have a chirality center, you have a chirality axis. The chirality axis, well, basically you have groups that are arranged around a certain molecule. And then if you look at the mirror image of that molecule and you try to superimpose the 2 mirror images, they are not superimposable. You don't have chirality center, you have a chirality axis. Very good example of that is biphenyl and allenes. We're going to talk about allenes later in chemistry 211 as well. Biphenyl, you have 2 phenyl rings. The phenyl is planar. The second phenyl is also planar. So basically you have this benzene ring and this benzene ring to be attached along the CC. You have a carbon-carbon, C single bond C. There is a free rotation between these 2 phenyl rings. However, if you put substituents here, A and B, they are different, and substituents here, X and Y, this rotation around the CC, it's going to be hindered. You do not have any more free rotation, because if you have free rotation, X has to pass in the neighborhood of A, and Y has to pass in the neighborhood of B. That will create steric hindrance. So you do not have this free rotation. That is an example of a chiral axis. The same thing for allenes. Allenes, you have C double bond C double bond C. Allenes where you have A different from B and X different from Y is also chiral. It has a chirality axis. You can think of it like you are having a screw, right-handed screw and left-handed screw. The right-handed screw is going to fit one hole that is different from the left-handed screw. Another example, well, before we go into another example, what you have here is a slow rotation. So you can have one enantiomer versus another enantiomer. These can be isolated differently. This is an example of what's called isomers or atropy isomers. These atropisomers, or atropisomers, it's better to be said that way, they are conformational isomers. Why I am saying conformational isomers? Because you are going from one enantiomer to the other enantiomer by rotation around C single bond C. Isn't that the definition of conformations? But this conformational change is hindered. It is hindered because of these groups. And that will be an example of atropisomers. Another example is the BNAP. This is an abbreviation of 2,2' bis diphenylphosphino 1,1' binaphthol. This is used as a catalysis in a hydrogenation reaction. Again, what you are having here is a naphthol. This is a naphthol ring. This is another naphthol ring. So you have this ring and this ring to be attached via a CC single bond C. When you are putting this diphenylphosphine group, which is huge, and another diphenylphosphine group, which is also big, these two groups, they will hinder the free rotation around the CC single bond, and that is another example of atropisomerism. With that, we are going to talk about reactions that create chirality center. And we are going to start from a very important fact. Optically inactive starting materials cannot generate optically active starting or optically active products. If I am starting, I have my reactants to be optically inactive, I cannot get product that is optically active. Which means, if I am starting from a racemic mixture, I should get racemic mixture. Right? If I am starting from a single enantiomer, then I might get a single enantiomer or I might get a racemic mixture. But if I am starting from a material that is optically inactive, I do not have any chirality center, not a racemic mixture. I am getting a product where I have a chiral center. Then I must be having a racemic mixture. Why? Because that is optically inactive. The only way I can get optically inactive product is to have a racemic mixture. I'm going to go over examples. For instance, this material is achiral. Why? I don't have any chiral center. Now we will learn in Chemistry 211 a reaction that is called an epoxidation reaction. We're going to talk about the mechanism of this reaction. We're going to talk about the stereochemistry of this reaction and about the features. That will be covered later in 211. Now we are only addressing stereochemistry and we are addressing the optical activity. We will learn that if you add a peroxy acid to an alkene, you will get what's called an epoxide, a three-member ring, heterocyclic compound where you are having an oxygen. Now in the product, you have a chiral center. Correct? What is the chiral center? This carbon. I am starting from optically inactive material. That means my product must be racemic mixture. It must be racemic mixture because I'm starting from optically inactive. I must be getting optically inactive. Now we say that this unit is prochiral. It's prochiral because after you are doing a reaction, you are achieving a chiral center. Now why do we have a racemic mixture? We will learn that the mechanism of this reaction involves the approach of the peroxy to the C double bond C. It will approach it either from the top or from the bottom. There is 50% chance that the peroxy acid is going to approach the C double bond C from the top, 50% is going to approach it from the bottom. That is going to lead into 50% R, 50% S. And therefore, you will get a racemic mixture. Now we refer to these two sides right here as enantiotopic sides. Why? Of the C double bond C. Because one side is giving me an R configuration, the other side is giving me an S. So the two faces of the C double bond C are enantiotopic faces. Another example we are going to learn in also in chapter 6 of Chemistry 211, the haloform reaction. You are having a C double bond, haloform, you will learn it in 212. The halohydrin. You will add the Br2 and water. So you have C double bond C and you are adding bromine and water. We're going to talk about the mechanism of this reaction. We're going to learn everything about this reaction. But for now, we are addressing the chirality and the optical activity. Is the starting material chiral? No, I don't have any chiral center. In the product, what I have is one chiral center. So the product must be chiral. I have one chiral center, not two chiral centers. One. So the product must be chiral because we learned that if you have one chiral center, the compound must be chiral. But the fact that I started from optically inactive materials, therefore I must have racemic mixture. So it is chiral, but it is racemic. Another reaction we will learn is the addition of HBr. All of these reactions, we're going to learn them in chapter 6 of Chemistry 211. So I have C double bond C, I add HBr. I have a chiral center, it must be racemic. Now, there are some reactions that will convert chiral reactants to chiral products. But you need always to remember, if you are starting from optically inactive materials, you must be getting optically inactive products. So if you are starting from a racemic, you will get a product that is also racemic. Because it is optically inactive, that is chiral, it must be optically inactive. Now what about some biochemical reactions? Well, biochemical reactions, they involve sometimes catalysts. The important thing here is the same. Optically inactive materials cannot lead to optically active materials. So there is no exception. Or probably there is one. What about this example? Do you think that this reaction is an exception of the rule optically inactive starting materials cannot lead to optically active starting material? What I have fumaric acid, I'm adding water and fumarase, and I am getting a product that is one enantiomer. It is optically active. What do you conclude?
Fumarase has an action on the other enantiomer.
Okay.
Maybe we attached it to fumarase, so the fumarase is actually optically active.
Okay. Anybody else? So I heard two answers till now. They are hinting on fumarase. Fumarase is playing a role. Of course, it is playing a role. It is in the reaction. What else?
Fumarase has a chirality point.
Good job. Absolutely correct. So that is not an exception. It's not an exception. What you can conclude here, fumarase must be chiral. You started from optically inactive. You are getting optically active. There must be some chiral, some optically active reactants in the reaction. Otherwise, you cannot get optically active products. This is optically inactive. Water is, of course, optically inactive. Fumarase must be optically active. That is our conclusion. Okay, this is a chiral. It is getting single enantiomer because fumarase is optically active. Now, a molecule with two chirality centers. Yes, sir.
So fumarase in this case has to be isolated, and it's not a racemic mixture.
Exactly. It must be optically active. Okay. Chiral molecules with two chirality centers. If I have now two chiral centers, how many stereoisomers can I make out of two chiral centers? Well, let's look at this example, for instance. the 2,3-dihydroxybutanoic acid, while carbon number 2 can be either an R or an S. And carbon number 3 can be either an R or an S. I have two chiral centers here. So the configurations I have are 2R, 3R, 2R, 3S, or 2S, 3R, or 2S, 3S. So I have four combinations. So I have 4 different stereoisomers. 4 combinations that will get me 4 stereoisomers. In fact, we are going to generate later. If you have n chiral centers, you are going to get 2 power n stereoisomers. Except if you have some kind of symmetry in the molecule, then the number will be less. We will get to that later. What is the relationship between these stereoisomers? The relationship 2R, 3R, and 2R, 3S are, well, let's go here first. 2R, 3R, and 2S, 3S are enantiomers. 2R, 3S, and 2S, 3R are enantiomers. Enantiomers, you will have the mirror image of every chiral center. Let me make up an example without even looking at the molecule. If I say I have a molecule with 5 chiral centers, where 2R, 3S, 4R, 5R, and 7S. Okay? What is the enantiomer of this molecule? 2S, 3R, 4S, 5S, and 7R. The enantiomer has the mirror image of every chiral center. Not most of them, every chiral center. The stereomers, they are stereoisomers that are not enantiomers. They are stereoisomers that are not enantiomers, which means that at least one chiral center is not mirror image. So let's generate a diastereomer here. So let's say I have 2R, 3S, 4R, 5S, 7R. What is the relation between these two? R, S, S, it is the same, SR. And there is one chiral center that is different. The relation between these two is diastereomers. If they are not enantiomers, they are what? They are stereoisomers that are not enantiomers. Therefore, they are diastereomers. As long as one chiral center is not a mirror image, then I have diastereomers. Okay? Enantiomers, you need to have a mirror image of every single chiral center. What is the relation between these two? Well, this is the same, this is the same, this is the same. One different. Diastereomers. What if I have the molecule, I am orienting it in a different way, and I am getting 2R, 3S, 4R, 5R, and 7S. What will be the relation of these two? Conformation, that's good. That's good. They are identical. You will definitely have in the exam 1 or 2 questions like this. So I will give you 2 molecules, and I will tell you what is the relation. I can tell you from now what are the choices. Okay? Enantiomers, diastereomers, conformations, probably I will put it, or if I don't put conformations, I put identical, resonance structures, constitutional isomers. You will have these choices, and you have 2 of these questions in the exam. How are we going to do it? Well, we are going to do it systematically. Let's say if I find R and S, if I get the mirror image of every one, then I know I have enantiomers. If I get one different, that will be diastereomers. If I get everything the same, that will be identical. Now, here are 4 different stereoisomers. And what I'm going to do here is an exercise. First, how to find the R and S for this molecule when I am looking at it in the Sawhorse projection. Let me see. So if this is H, OH, CH3. Yep, perfect. Okay. So that we follow the model, I am going to tell you the color, what every color represents. What is the group? So the red is an OH group. The white is a hydrogen. The green, not green, this is blue. The blue is a CO2H group, and the black is a carbon. Fine? What I just built right here is a model for this one. Okay? Let's see. This is OH. This is hydrogen. This is CH3. In the back, this is carbon. This is CO2H. This is hydrogen. This is OH. Okay? What I would like to do first here is to find the R and S configuration. What you have on the slide, the correct R and S configuration of all 4 stereoisomers. Okay? I want to find the chirality, the absolute configuration of this carbon. From where you are standing, or from where you are sitting, you are looking at the molecule from the wrong direction. Why? Because the lowest priority group is hydrogen. It's not away from you. Now it is away from you. Okay? So I'm going to be standing the same way you are sitting so that we follow the configuration. We find the configuration. Now around this carbon, where is the highest priority group? OH. What is the second? This carbon is attached to carbon. Well, I'm sorry. This carbon is attached to oxygen because we have to put it in decreasing atomic number, right? This carbon is attached to oxygen, carbon, hydrogen. This carbon is attached to 3 hydrogen. So what do I have then? 1, 2, 3. Hydrogen is away from me. Am I going clockwise or counterclockwise? Clockwise. It is an R configuration. Okay? Now I'm going to find the configuration of this carbon. This is carbon. This is oxygen. This is carbon. So which one is the highest priority? Oxygen. Now this carbon is bonded to oxygen, oxygen, hydrogen. This carbon is bonded to oxygen, carbon. So where is this one? So that is going 1. Now I am orienting it. This is 1, 2, 3. Am I going clockwise or counterclockwise? Therefore, this is an S configuration. If you are looking at the molecule and you are drawing it, and you are drawing it on a piece of paper, you might need to look at the paper like this so that you can find the configuration. But I'm going to give you a hint later so that you don't need to rotate that, and you can find the R and S very easily, even if you are drawing it where the hydrogen, thank you, is in the plane. So please practice and find out the R and S configuration of all of these carbons. Now, this has a specific rotation of minus 9.5. This has a specific rotation of plus 9.5. The relation between these two is an enantiomeric relation. These two are enantiomers. And these two are enantiomers. While the relation between this one and this one is what? The stereo. I have RS. I have RS and I have SS, diastereomers. So not all relations are enantiomers. Stereoisomers that are not enantiomers are diastereomers. Now the second exercise that I want to do is to go into a Fischer projection. We will keep the same thing right here. I want to take this molecule. So let's say I have it like that. I want to take this molecule and put it in a Fischer projection. What did we agree about Fischer projection? The horizontal bonds are towards you and the vertical bonds are away. The first thing you need to do when you are going from the sawhorse into a Fischer projection, you need to rotate the molecule so that all bonds are eclipsing each other. You cannot go from this sawhorse into a Fischer unless you rotate so that the bonds are eclipsing each other. And you need to look at the molecule from the angle where the horizontal bonds are towards you and the vertical bonds are away from you. Now you can make your life very complicated or you can make it very simple. Let me start with the complicated. You can look at the molecule like this. That's fine. These are towards you. These are away from you. And then when you are putting it like that, you are doing this so that you are putting it. Right? It gets worse. You can look at it from here like this. Then you will have these bonds are towards you and these bonds are away from you. Do you want to go into the simple or do you want to keep looking at the complicated? The simplest way is to look at the molecule from the top. You look at the molecule from the top and you just step on the molecule. When you are stepping on the molecule, you are having the Fischer projection. Why? When you're stepping on the molecule, this is going to flatten and these are going to be towards you. The best way, the easiest way, is to look at the molecule from the top. Step on the molecule, you get your Fischer projection. Now I'm going to throw this model aside. And I'm going to do it paper chemistry. So I'm going to draw a structure and I'm going to do it. How I am going to step on the molecule and how I am going to go into a Fischer projection. That is a very important exercise. And I usually do it in the lecture so that you don't make a mistake. So let me draw a structure on the board. Well, you know what? What we are going to do, we are going to take that molecule into the Fischer projection, and then we are going to find R and S configuration in the Fischer projection, and we want to make sure that the R and S in the Fischer projection are the same as in the sawhorse, because if they are not, we made a mistake. So for that reason, I am going to go back in the slide, and I will just draw the same model that we practiced. Now I am going to do the exercise. We agreed I need to rotate the molecule so that the bonds are eclipsing each other. And we want to rotate it so that I have the bonds that are horizontal towards me and the vertical are away from me. So when I'm going into the sawhorse, I need to rotate the front carbon or the back carbon. As I told you, the simplest way. Do I rotate the front carbon or the back carbon? The back carbon. Because the front, it's already directed towards me. The OH and the hydrogen are towards me and the CH is away. So when I am rotating, I am getting in the back, it is the same, OH, H. In the front, it is the same, I am rotating in the back. Now, do I rotate clockwise or counterclockwise in the back? It doesn't make any difference. That's the beauty about it. It doesn't make any difference. And we are going to do that exercise as well. If you rotate clockwise or counterclockwise, you will get exactly the same configuration. The important thing is to put the bonds to be eclipsing each other. Now I am going to rotate. Let me make this a little longer so that we see it. I need the bonds to be eclipsing each other. Now, what I strongly encourage you is to do the rotation only once. Yani like you're rotating only 60 degrees. So that you follow the groups. So if you are rotating clockwise, only once, what will be the group here? OH. What will be the group here? CO2H or hydrogen? CO2H. I rotated only once. That will be CO2H. And right here, hydrogen. Now I am going to step on the molecule to get the Fischer projection. When I am stepping on the molecule, what will be this group? Correct. What will be this group? CO2H. When I am stepping on the molecule, the group on my right is CO2H. What is the group on my left? Hydrogen, for that chiral center. Right? Right here. OH. H. CH3. Well, I have OH and CO2H to be eclipsing each other. I have hydrogen and hydrogen to be eclipsing each other. And I have OH and CH3 to be eclipsing each other. Okay? Now let's find R and S. This is the second part of the exercise. How do we find R and S in a Fischer? It is the easiest to find R and S in a Fischer projection. Why? Because you already know that all bonds are either towards you or away from you. Okay? Now, for this chiral center is attached to an oxygen, OH, CO2H, this carbon, and hydrogen. Where is priority number 1? OH. Where is priority number 2? I have carbon bonded to oxygen, oxygen. I have a carbon bonded to oxygen, carbon. So where is, this is 2 and this is 3. Now, wait. We need the molecule to be oriented so that the lowest priority group is away from us. We're not going to do that. Why? Hydrogen is where? It's towards you. So you're looking at the molecule from the wrong direction. Rotating it is much harder than doing a very simple exercise. You know that the hydrogen is towards you. That means you are looking at the molecule from the opposite side. You find the configuration. If it is R, it's S. If it is S, you switch it into an R. Okay? Because to look at the molecule from the wrong side will get you the wrong enantiomer. To look at this molecule from the right side, you need to be inside the board on the other room so that you see it. So that 1, 2, 3, are you going clockwise or counterclockwise? Clockwise. Usually the steps that I do, I'm going clockwise. Therefore, it is an R. Is hydrogen towards me or away from me? Towards me, therefore, the configuration is S. So this is an S configuration. Now what I will do, I will erase 1, 2, and 3. Why? Because now I am going to look at the chirality center, at this chiral center. And I don't want the 1, 2, 3 before to confuse me. Now around this carbon, I have OH, carbon, carbon. So this is 1. Where is 2? Where is 3? Right here. 1, 2, 3. Am I going clockwise or counterclockwise? Counterclockwise. It is an S, but hydrogen is towards me, therefore it is an R. SR. Now I told you earlier, it doesn't make any difference whether you rotate it clockwise or counterclockwise. I'll prove it. You know what? While we are proving it, I'm going to ask you a question. What is the relation between these two structures? What is the relation between these two structures? Choices you have in the exam. Enantiomers, diastereomers, identical, resonance structures, and 5 constitutional isomers. Okay. So what is the relation between these two structures? One second, please. Yes? No, it is CO2H. This is CO2H and this is CO2H. Okay, this is my question first. Let's solve the question and then I will tell you about the hint. How do you find the relation between these two? You find R and S, right? If you are having R and S to be exactly the same at all carbons, what will be the relation? Identical. If you find R and S to be opposite for every carbon, what will be the relation? Enantiomers. And if you have one of them to be different, what will be the relation? The stereo. But if we are talking here about stereoisomers, right? You need to make sure that all connectivity is the same. Because if the connectivity is different, what will be the relation? Constitutional isomers. Okay? And here, of course, we don't have any resonance structures as an option. Fine. So we already found the R and S configuration for this one. Now what will be the configuration of this carbon? It's exactly the same like here. Do I really need to do it? It is the same. So this is definitely an R. Now what about this one? This is 1. This is carbon bonded. This is 2. And this is 3. 1, 2, 3. Am I going clockwise or counterclockwise? Clockwise. This is an R. Hydrogen is towards you. Therefore, this is an S. So what is the relation? Identical. You have SR and SR. When I was developing this question right now in front of you, as I will do it for the exams, I made the question so that they are identical without solving R and S. How did I do it?
Just rotate.
Let me tell you about Fischer projection. Anytime you rotate the 3 groups, clockwise or counterclockwise, the configuration is the same. And I just proved it to you right here. What did I do when I was developing the question? I moved CO2H over here. OH will be here. Hydrogen will be here. Well, now I did another one. I moved the CO2H over here. OH will be here. Hydrogen will be here. The configuration is the same. That is exactly if I have done this rotation in an opposite way. Okay? In a Fischer projection, anytime you rotate the 3 groups clockwise or counterclockwise, the R remains R, the S remains R. Anytime you rotate 2 groups, R becomes S, S becomes R. I prove it. So what is the relation between this one now and this one? This is OH, hydrogen, CH3, hydrogen, OH, CO2H. The configuration of this carbon is exactly the same, right? This is an S. Now this is 1, this is 2, this is 3. I am going clockwise or counterclockwise? Clockwise. Hydrogen is towards you. This is an S. So I have SS and I have SR. What is the relation? Diastereomers. Diastereomers. Because I have one chiral center to be different. Okay, now you can generate the questions for the exam about this. Now what I will do in the exam, either I will give you 2 Fischers, or I will give you 1 Newman and 1 Fischer, or I will give you 1 Sohorst and 1 Newman, or 1 Sohorst and 1 Fischer, or whatever. And we are going to have a couple of these questions in the clicker session while we're practicing. Okay. Do you have any questions about this?
Can you just repeat what you said if you rotate 2 groups?
Right here, what I did when I generated this, I put this OH over here and the hydrogen over here. And right away, I knew before I put it that the configuration is going to be an S because I switched to group. So anytime you switch to groups, you will have an S. Okay, apparently you're enjoying this and you don't want to leave. Let me make another one. Okay, look. What is the relation, for instance, between these two? Now you can do R and S, and fine. But right away, I know that the relation is identical. Before I even did the R and S. Why? Because I moved these two groups, and I moved these two groups. Right? So R becomes S, and then S becomes R. Therefore, I am back to the start. So what is the relation between these two? It's an identical. You switch two groups, the R becomes S, S becomes R. In this particular example, because you have only one chiral center, you have only two options. Either enantiomers or identical. You cannot have diastereomers. You need to have at least two chiral centers to have diastereomers. Okay? Thank you.